Welcome everybody, my name is Thorsten Höffler. Welcome to my presentation on arming GPUs on the memory subsystem of the Grace Hopper GH200 Superchip. This is a presentation I made for the ARM workshop at the Supercomputing Asia 2025 conference in Singapore, and I want to present it here to you as well. It's a great paper that was driven by Luigi Fusco and many members of my team, really aiming at analyzing the details of the GH200 Superchip. And we did find some interesting Easter eggs. Easter was just a while ago, and we were quite surprised what happened when we looked at this in great detail. So bear with me, and you will be finding a lot of interesting insights into this chip. I would also recommend you to look through the paper for all the technical details that I don't have enough time to explain in this particular talk. So what is the GH200 Superchip? It is one of the first chips where really CPU and GPU are integrated into the same package and connected with an extremely high performance interconnect that also extends to a system, larger system-wide scale, namely 4 of those chips interconnected with a high performance interconnect, and then even enabling a wider connectivity to tens of thousands of those chips. So on the left side here, well, in this die shot, or actually package shot, we see a Grace CPU that is an ARM-based CPU with SVE extensions, was specifically made for that purpose, and the Hopper H100 essentially GPU. So now these two are connected by an interconnect that is called NVLink C2C, which has 450 gigabyte per second per direction, so 900 gigabyte per second total. It's not to be confused with the pre-existing NVLink that connects GPUs. It is a specialized interconnect that only connects the Grace CPU with the Hopper GPU, but it fits into the NVLink family. Then the Grace CPU itself is equipped with lots of LPDDR5 memory, which has a bandwidth of 500 gigabyte per second, so not super high, but it is a very high capacity in many of the configurations. Of course, you can configure that chip in in a wide variety of different configurations. So the Hopper GPU itself is equipped with 4 terabyte per second HBM, so high bandwidth memory, version 3, and at the end you can put up to nearly 20 terabyte per second into a shared memory domain. So this is quite an interesting chip, sorry, not per second, but 20 terabyte total into a shared memory domain. But now you of course have to program this thing as a NUMA device. So we can see here NUMA region 0 is the Grace CPU. Now NUMA region 4, if you run this with Linux, is the Hopper GPU. So now you wonder, okay, where are these other 3 NUMA regions? Well, they are in the other 3 chips. So Grace CPU 1 in chip 1 has NUMA region 1, in chip 2 has NUMA region 2, in chip 3 has NUMA region 3. These are all connected into a cache coherent global system. So now the Hopper GPUs, you see that this is now NUMA region 4 here, so it counts first the CPUs, then the GPUs, and then it goes in strides of 8 due to the internal structure of the GPU, 12, 20, and 28. So now there is an interconnect that connects all the GPUs. So each of these CPUs and GPUs are connected with NVLink C2C. The GPUs themselves are connected with the traditional NVLink, which gives you 150 gigabyte per second per direction bandwidth, so 300 bidirectional times 3 gets you again 900 gigabyte per second. But now note that between any pair of 2 GPUs, you would only get 150 gigabyte per second. The total bandwidth leaving one GPU going to 3 different destinations is 300 gigabyte per second bidirectional. So this is a weaker link than the on-package link, which is of course clear because it's a larger distance you have to span. Now, the surprise interconnect that wasn't quite announced in the documentation and still is very sparsely documented is another interconnect that actually doesn't really have a name, but we call it the Grace interconnect. The Grace interconnect is the interconnect that connects all these CPUs. If you now communicate from CPU 1 to CPU 2, for example, you would be using the Grace interconnect. That interconnect gets you 150 gigabyte per second, and that is quite important because that is a global speed of 150 gigabyte per second. So it's not 900 gigabyte per second leaving the chip, but only 150 gigabyte per second leaving each chip, so it's significantly slower. Talking about slower, well, there is the global interconnect, which is then connecting the different boxes, so to say, so the different chip groups, and that is in many cases the slingshot interconnect, like in our Alps system, and that is of course connected by long wires with switches, and that is significantly slower than the in-package or in-rack interconnects, of course. So now, if you now look at the the latencies and the different latencies across the different chips, it gets quite interesting. So now, first of all, what is the access latency to memory? Well, if you access from the Grace CPU, you would actually get a bandwidth of about 100 gigabyte per second to the HBM of a peer, so to the HBM of another GPU. You would get 310 something gigabyte per second to the local HBM, and you would get the promised 500 gigabyte per second to the local DDR, and you would get about 90 gigabyte per second to a remote DDR and a remote peer DDR. So you already see that this is the limit of this, this Grace interconnect here for this access. Right? So you would actually expect remotely, given all the bandwidths, you should be able to go through NVLink C2C to the NVLink to the other side at least a 300 gigabyte per second, but you can't because of these limitations. And then if you access memory from the Hopper device, which is most likely what you do because that's the high performance device here. So the HBM gets you nearly 4 terabyte per second as it's advertised, so that's perfect. But now if you look at the bandwidth for local DDR, which is about 500, but if you actually go to HBM at a peer, it's lower, and if you go to DDR at a peer, it's also lower. You can also see on the other axis here is the latency. So the further you go, the higher the latency gets, and you see the same here from the Hopper, where for the Hopper the base latency is higher. So the DDR memory accessible to the Grace, that's local to the Grace, is less than 200 nanoseconds. For the Hopper, the minimum latency you would get is more like 380 nanoseconds going through local HBM, because of course it's a throughput device, it's not a latency device, so that is perfectly expected. So it's already complicated to figure out. So in some sense, what we can conclude is that local HBM and local DDR perform well, and as you go remote through the various protocols or various links that I talked about, you have to be a little bit more careful. So now what we found is that the NVLink C2C itself achieves only about 70% of the peak, which is probably good, but then the Grace interconnect, the highest we've seen, is only 55% of the peak, because that is a chip-to-chip interconnect that runs a cache coherence protocol that was not disclosed which one exactly, but I would assume one of the standard ones. So that is an interesting one. But if you now look at the different memories and the different PUs, you can see that there is a difference in how to access this memories, again summarized here. So you could either go from a Grace and a Hopper to these different memories, and you would see that if you go from a Hopper to the local HBM, you get 4 terabyte per second in theory. And then here you see the other theory tables, which is why this is called bounds. So it's essentially what is the maximum you would expect. And you already see that some links are relatively low. So for example, if you go from Hopper to another remote HBM, you're only expecting about 150 gigabyte per second, because that's only one connectivity. So when you read 900 gigabyte per second NVLink, well, that's to all of them, but you would only access one specific one unless you play tricks that you somehow distribute your memory access through multiple target GPUs. In this case, you would have 3 in your package. So now, if you want to copy now, if you look at copy bounds, if you wanted to copy, for example, from a Grace chip, from a DDR to HBM, the maximum you could achieve in theory is 450 gigabyte per second. And if you wanted to copy, let's say, from a local DDR to a remote DDR, the maximum you could achieve is 150 gigabyte per second. So you see, there's also a huge discrepancy between the different source destination pairs and also who issues the copy, because it's going to be very different if the Hopper GPU issues the copy. So here in the Hopper GPU, you can actually achieve a 2 terabyte per second local copy from HBM to HBM. But then if you look, as soon as you traverse any of these links, you would also see again, well, this is significantly lower. So usually more than a factor of 10 lower to go remotely or even anywhere close. And these are the bounds, these are the theoretical numbers, and you can see some of the practical measured numbers here. So it's already very, very complicated. So you have to look at who issues or which device issues the copy and what are the source and the target pieces here. So now you could now argue that you should also measure this. Well, this is relatively easy to measure because it's all a unified memory space. So you could just write a copy benchmark, which is what we did specifically. Luigi did this, and now it gets quite interesting. So now it's actually, we have here the source, and we have various different types of memory, and we even have different types of allocation of how this memory is allocated, because that unfortunately plays a role. So whether you use CUDA malloc or NUMA alloc on node, or there are various different calls, I will get to a table in a couple of minutes. And here you see that if you copy from device to device, for example, in practice you should be getting 2 terabyte per second, you get about 1.4 terabyte per second, that's not too bad. But if you allocate the memory in managed mode, or if you allocate both memories in managed mode, source and destination memory, then you only get 1300 gigabyte per second, which is relatively low. And then you could, I don't want to go through the whole table, but one shocking thing is if you have a DDR remote, if you copy from remote DDR to remote DDR, you have to live with a 5 gigabyte per second, nearly 100x, no, actually nearly 1,000 times, or something like 800 times slower than a copy would be. Actually, sorry, not 800 times, 400 times slower than a copy would be on device. So it's very important to understand where you're copying from and where you're copying to on this device, and how you allocated the memory. Right? This is even more important. So now, of course, when you issue these copies, you must use multiple copy engines. So how do you program these copy engines? That's typically with threads. So each thread occupies a small number of copy engines, usually one. And now the more threads you have, the higher bandwidth you get. So for example, if you look at the Grace device, and we are now performing an intra-node copy, if you look at the throughput and increase the number of threads, you can see that this goes up, and these are now different intra-node memories again, HBM to HBM, HBM to DDR, DDR to HBM, and DDR to DDR. You can see here the DDR to DDR is saturating at about 220 gigabyte per second. We are expecting 250 because it's half of the 500 gigabytes, so that's not too bad. But you have to at least use 40 threads, or actually at least use like something like 30 threads to cross the 200 gigabyte per second boundary. You can now look at these other things. For example, the fastest mode you can copy is DDR to HBM, so from my local DDR into GPU, limited by the NVLink C2C interconnect would be 450 gigabyte per second. We're achieving up to 300 gigabyte per second if we use a sufficient number of threads. On the Hopper device, it's the same. Instead of threads, we're talking about thread blocks in this case. And so we have to use full warps. And the idea here is that we can actually copy with from HBM to HBM at nearly 1,500 gigabyte per second, so 1.5 terabyte per second, as I mentioned before. But again, you need a sufficient number of threads to do this. So in this case, you need at least 100 thread blocks to actually perform the copy. Again, lots of data. You need to understand how to go forward on this device. Now the question is, what is my latency? Because we talked about latency before. Now, if I do a single thread copy, what is my minimum latency I can achieve? And so here is again, who issues this copy is very important. So if the Grace issues a copy, oh no, actually in this case it's a read access, I believe, and so you can look at the Grace and the Hopper. So reading from DDR memory is going to take 170 nanoseconds. That's the fastest we have in the system. So actually the lowest latency memory on the system is the LPDDR accessed from the Grace CPU. Going to HBM is nearly 800 nanoseconds. Going to DDR of a remote node is actually faster, so that's not too bad. And going to HBM of a remote node, of course, you now have to go through multiple links, is going to be nearly 1 microsecond. That's a lot, because you can, in the good old days, you could go through multiple racks in 1 microsecond, actually. But today, the latency has been driven up for a while. The Hopper GPU is, of course, not latency optimized, which means if we wanted to access memory in the HBM, we pay more than twice as much, or actually about twice as much as the CPU latency. Going to the DDR memory that is locally attached with with NVLink C2C is about 800 nanoseconds, so nearly 1 microsecond. And going to a DDR of a remote node, or even the HBM of a remote node, is more than 1 microsecond again. So those, keep this in mind. Latencies are very critical. Of course, GPUs overlap the latency through the SIMT architecture that rotates warps, and the memory controller is going to take care of it if we have enough parallelism. But here it's just a single thread. But now the question is, does it matter which peer? Does it matter who I'm accessing? And GPUs or throughput devices. So now, if you actually look at this, this is already quite complex when we are accessing this here, right? So we go from the Grace. if you, for example, go to the HBM of a remote node, what would be the obvious path? We would go from the Grace to the local Hopper GPU, then connect through NVLink C2C, then connect through NVLink to a remote GPU, and then read it back through those buses. Right? So this is a possible link. I believe that's the link that's going to be used. You could also go through the Grace interconnect and then go locally, but I believe that's not what's happening in the real system. Of course, we don't know. We are not. You would need to ask the architects of the system. Okay, so now if we go into more detail, does it depend on the peers? And actually it does, unfortunately. So it really, the latency really depends on who is talking to whom. So if Grace 0 is talking to Grace 0, you have 100 nanosecond latency, which is basically your local memory access. If Grace 0 is talking to Grace 1, it is 127 nanoseconds. It's not too bad. But if, oh no, actually, sorry. So if Grace 0 is talking to Grace 1, it's 700 nanoseconds. But now you may think that this is the DDR memory. But now if Grace 1 talks to Grace 2, it's more than a microsecond. So actually, it's asymmetric now. So Grace 0 is connected better to Grace 1 than Grace 1 is connected to Grace 2. And you can also see here Grace 0, here is again with the HBM, it's again the same. So you see really that there is an asymmetry in the system. And I don't want to point out all the details here, but you can also see the Hopper 0 to Grace 1 and Hopper 1 to Grace 2. There's nearly a 50% latency overhead. And so somehow the system is asymmetric, and you need to understand which peers are communicating. That is interesting to optimize if you care about these details. But now the question is, well, now we talked about latency, very small buffers, single thread access. What am I doing if I'm accessing bigger buffers? Well, it's another question. Does the access size actually matter? And of course it does, because on a Grace CPU, it's a standard cached system. So the larger the buffer you access, the more you will go into cache. And here you see various cache sizes and that form boundaries. This is just a zoomed in diagram here. So this is actually the CPU L1 cache size, the L2 cache size. You see it's jumping up. This, of course, assuming reuse here. The L3 cache size is here, as you can see here. And as you're falling out of L3 cache, you're going to much higher latencies. On the GPU, it's very similar. GPUs these days also have L1 and L2 cache, which is marked here. You can see a very clear increase going from L1 to L2. You can also see a very clear increase leaving L2 and essentially now being bound by the memory bandwidth and memory latencies. So this is also quite challenging to understand and to program in if you want to go into that much detail. But another question is, does this all matter for real applications? Because most people don't know about these technical details of the exact latencies and bandwidths between all the devices. And this is a particularly complicated chip. But we also looked at just matrix multiply, one of the most important workloads for deep learning. And we looked at two square matrices of size 4 GB each, and we put them into different locations. So we put one matrix into HBM, for example, in this case, another one into HBM, and then we get 384 gigaflop per second with a TF32, or maybe even teraflop per second, I'm not 100% sure. and if you put them in different memories, so for example, if you put them both in DDR, in remote DDR memory, then the performance drops significantly, right? So of course, at the end, many applications are memory bandwidth bound. So here we see a discrepancy from more than 600 to 10. So that's a factor of 60 in this case. Or here we see 51 to 3. That's a factor of a little bit more than 10. So it really depends on where you put your operands. So you need to stage these operands into the right memory. Of course, it's a typical memory hierarchy question. These slower memories, like the DDR memory, gets slower, but they get larger. And now the remote memory is even larger. If you want to access the full 20 terabyte of the device, you need to go remotely, but then it's of course even slower. So that is something very important to consider. Then you may wonder, okay, well, at least the intra-node communication should be simple. Unfortunately, that's also not simple. If you go to unidirectional, bidirectional communication, it matters a lot how many processes are actually communicating. Very similar to the threads. A single process cannot fill the pipe of this device, of this powerful device. You need multiple processes to achieve the full bandwidth, in this case up to 4, and at 4 processes you achieve the peak bandwidth of 100 gigabyte per second of the slingshot interconnect. If you use only one process, you may be limited to only 25 gigabyte per second. And it's very similar in the bidirectional case. So there is much more complexity to be said in the paper. There are many, many more diagrams and actually various copy paths that are getting quite complicated if you communicate between these different memories. If you solve, if you assume that's really a flat address space, then your performance is pretty much very, very low if you're unlucky. So you really have to understand these copy paths to be a proficient programmer of this device. Then what's even more complicated is these how you allocate the memories. There's system allocated memory, device allocated memory with CUDA malloc. There is managed memory, CUDA malloc managed. There is pinned memory, which after you allocate it, you pin it. Or you use these calls CUDA malloc host and CUDA host alloc. And they're all quite different. They're all placed in different modes. Like first touch, you can actually specify it for some of those with a NUMA alloc on node. CUDA malloc goes by default into HBM. Then you have again first touch placement. And many, many, many different GPU translation models, how it's actually finding the pages, how it's finding the physical address. You have different page sizes, and you have various support for automatic migration, even depending on the CUDA version. So this is now extremely complex. Now it depends on which is the device that's issuing the call, where are the operands located in which memories, and how did I even allocate this memory? So how can I program this thing? Well, that's something you need to figure out yourself and to understand with the Grace Hopper Superchip paper that is more like a performance documentation that we have written, and I highly recommend flipping through it if you're a performance engineer working on this device. But now I want to give you another option for doing this. Let somebody else do it. And let somebody else do it using performance metaprogramming. That's the technique that we have developed in my group for quite a long time, where the idea is that we have a domain scientist who really works on the application itself, who doesn't care about all these details, because you need another scientist, like an applied scientist or actually a performance engineer, to figure out all of these details. In our framework of the performance metaprogramming, the domain scientist writes the code, the applied scientist translates it into some representation that is easy to understand for a performance engineer. Well, typically the performance engineer doesn't understand what the application does, but the performance engineer understands the data flow in a different representation, a parametric program graph representation, where the performance engineer now can worry about where to place these memories and how the data flows through the system. And at the end, we output GPU code, CPU code, and also FPGA code. But what I talked about here really requires only CPU code and GPU code, and it would be in tandem, and it would allow the performance engineer, without any modifications to the original source code, map memories, variables to the right device. And at the end, this leads to very simple programming at the scientist, more complex programming at the performance engineer, but many of those are reusable meta programs. Similar structures will be working across similar applications. So if I have one stencil application, the meta program may actually work even for another stencil application. And at the end, it's going to generate tens of thousands of source lines of code, of CUDA code, that nobody really wants to look at, of course, because they can get quite complex. So now, as I mentioned, this talk is designed for the ARM for Science workshop. So how is this all different from x86 or any other CPU or GPU? Of course, the system I talked about, Grace Hopper, is an ARM system, but actually this all applies to all the other systems as well, because we have to worry about performance portability. Performance metaprogramming just fixes the programming for scientists and end users, but how do we deploy software now? How do we, once we have the performance metaprogram, how do we deploy this forward? And inspired by cloud computing, I want to present you another idea that we are pushing in my group to actually have a performance portable deployment model, really similar to cloud computing. And the idea is to have performance portable containers. They could be taking advantage of performance metaprogramming, but they could also use the established library approach to relink. So how does that work? It's something that we call acceleration as a service, and it was published in the Computing in Science and Engineering journal, and really with many, many authors, trying to understand what a good model would be to enable this. And the idea is that we take the best of the two worlds, high performance computing, which really stands for high performance first, so we want to make optimization the best, and cloud computing, which really stands for the ecosystem and simplicity, accessibility first. So easy deployment, CI/CD. Both of those are not necessarily in conflict, but these two different communities, they have been focusing on two different things. And we really want to enable both of those communities to move forward together, to merge these central thoughts into the same system, which we really the key of this is performance portable containers, which is an infrastructure question. We of course need high performance communication as well as high performance allocations and accounting, because at the end somebody needs to pay for it, to enable this model. So, and in some sense, this enables a high performance cloud computing with long running jobs. So very similar to function as a service, but longer running jobs and parallel jobs that are actually executing fast. So here you see again an overview of how this could work. So from cloud computing come the idea of virtual machines. From supercomputing come the idea of specialized compilation, a specialized source code, be it libraries or even recompilation at deployment time. And at the end, we get all of these wonderful features, portability and DevOps productivity. So basically the best of both worlds in this SaaS idea. So at the high level, what we define several layers. And the idea is at the very bottom layer, we of course have cloud providers and HPC service providers. They're at the same level. So they're the providers that give us the hardware, so infrastructure as a service to some extent. Then on top of this, there should be a standard portable container API. It could be very similar to the OCI container API. It would be great. And then the generic containers usually come with a base operating system layer. That's nothing new. But the SaaS accelerated containers would basically have an accelerated compute, communication, and I/O library interface that would enable at deployment time to specialize to the target system. That interface has to, of course, be system specific, so it has to be tuned to HPE and Intel, which is typically not the case for generic containers. These generic containers would deploy on, let's say, any x86 system. This one would deploy differently on an InfiniBand-based HPE system than on a Slingshot-based HPE system. Right? So this is really the difference. Of course, these would be maintained, both layers would be maintained by the provider, the base layer as well as the performance portability layer. And then we have many, many platforms on top of this, either service platforms or simulation platforms, which would be maintained by the community because they're now domain specific. So you would be coming with your portable climate icon container, for example, and would deploy it on those systems. And automatically at each provider, you would link different system specific libraries. Or in the case of icon, you would probably recompile different pieces of the code, maybe with days, as I mentioned earlier, to fit to the target system. That's the vision of acceleration as a service. So let me now conclude. I told you about the Grace Hopper Superchip, which is quite a complex architecture. I told you about the complexity is really mind-blowing because even it's not symmetric. I mean, depending on your communication between Grace 0 and Grace 1 or Grace 1 and Grace 2, you will get different latencies and different bandwidths. I told you one solution that we could employ this performance metaprogramming to manage this huge complexity. And at the end, even at deployment, we could be benefiting from novel ideas going forward. So this is a true community effort. I would recommend you reading this paper if you're worried about all the details. And with that, I would like to close my talk and thank you.